So we are going to now see a second version for fast exponentiation, which can be referred to as a right to left algorithm. We'll start from here. So again, we try to compute 3 to the power 77. We start by writing the exponent 77 as in binary. And in this version of fast exponentiation, we start with this bit over here. So one. We are going to have two variables, a variable d, which stores the current result, and the variable h, which is storing the result of 3 at the power corresponding to the current bit. At the very beginning, 3 to the power 1, it's 3. So when we encounter this bit of 1, we are going to multiply the previous bit 3 with the current value 1, because we have a 1 over here, and we get the current value being equal to 3. And we are going to prepare h for the next position, 0, by squaring it. 3 squared equals 9. Mod 11 is 9. Next, we are considering the second bit, 0. So bit 0 tells that 3 of this exponent is not at all used in our result. So we keep d as it was, and we prepare h for the next exponent, which will be 9 squared. 9 squared is 81, mod 11, it's 77 plus 4. So we extend the exponent one position to the left, it's a 1. 1 means that the current exponent, the current base is used, so 3 at the power 4 at power that it's 4 over there was equal to 4 mod 11. So we are going to multiply 4 with 3, and we get 12, which is equal to 1. And we are going to prepare the base for the next exponent by computing 4 squared, which is 16. Mod 11, it's 5. We extend once more the exponent to the left, we have 1 more 1. Here we computed 3 times 4 equals 12, which is equal to 1 mod 11. Yeah.
So back at the top, was that 4 squared?
This was 4 squared, which is 16, which mod 11 is 5. Okay. Then, because we got 1 more 1 over there, means this 5, it's aggregated into the current result. So you get here 5 times 1 equals 5. And we prepare our 5 for the next computation by computing 5 squared equals 25, which mod 11 is equal to 22 plus 3. We expand again the exponent to the left, we get a 0. 0 means this 3 is not used. the current base, so we keep 5 unchanged. And we prepare the base for the next computation. It becomes 3 squared, which is 9. One more expansion to the left. It's a bit of 0. Which means that the 5 remains unchanged, the base is not used. Okay? And the exponent is squared, 9 squared. Again, it's 81, which is again 4. Right? One more expansion to the left. We encounter 1, which means that we integrate this 4 into the result. We get 20, which is 11 plus 9. And you could optionally, but we won't use anywhere, compute 4 squared here, which is the algorithm does it if you don't over-optimize. And it's going to be 16, which is 5, but it's not used anywhere. The result is 9 because we finished. Sorry. No, we are not done. Yeah, you are done. So the result is 9 mod 11. Yes?
So we don't worry about the leading 0 when we're doing the right to left version.
In this case, no. It wouldn't change, you know. If you would worry about it, an extra 0 here means that you copy the result unchanged. Other questions?
Yes. You said RSA is dependent on exponential